Hello class, it's Miss Peterson here again, and today we're going to be doing 7.5 notes, which is operations with radical expressions. So just starting off here, let's see, we have some properties that we need to talk about. So the first property is our product property, which is the nth root of AB is equal to the nth root of A times the nth root of B. So we can take any set of radicals and split them apart like they did here. All right, so for example, let's say we have the square root of 16. We can split this apart into the square root of 4 times the square root of 4, because we know that 4 times 4 is 16. So this is square root of 4 is 2, and then we have times 2. So the square root is obviously going to be 4. We can also split this apart with different indexes, not always 2, so sometimes 3. So if we have the cube root of 27 we can really write as 3 times 3 times 3. So if we split this apart, we have the cube root of 3 times the cube root of 3 times the cube root of 3. Oh, never mind. Hold on. All right, so ignore that last example that I was trying to do here. My mistake. So focus on what we have here. Just know that we can split apart a product underneath the radical and pull it into a couple different radicals. The other property that we have is the quotient property. So the nth root of a over b is equal to the nth root of a over the nth root of b if all roots are defined and b does not equal 0. B cannot equal 0 because it's on the bottom of a fraction. So we know that if 0 is at the bottom of a fraction, it's undefined, it doesn't exist. So a couple examples here. If we have the cube root of 54 over 2, we can rewrite this as the cube root of 54 over the cube root of 2. Let me just move the screen down a little bit to give me some room to work. So if we simplify this, so 54 we can actually turn into 27 times 2. And here we still have the cube root of 2. So 27, we know that we can split apart this top here. So if we move over here to give myself a little room, we have the cube root of 27 if we break apart by the product property times the cube root of 2. And this is all over the cube root of 2. All right, so we have cube root of 2 on top, cube root of 2 on the bottom. These cancel out to 1 and we're left with the cube root of 27. We know that the cube root of 27 is equal to 3, and that's your answer. So basically, for any real numbers a and b and any integer greater than 1, the following properties, the product property and quotient property, will hold true. So a couple things to remember when simplifying a radical. Stop. No radicals in the bottom of a fraction. So we have the nth root of x over y. We cannot have radicals in the denominator of a fraction. So in order to get rid of these, we're going to multiply the numerator and denominator by a quantity so that the number underneath the radical is an exact root. So we'll do a couple examples of these. So rationalizing the denominator. So to rationalize the denominator, like I said, you need to multiply the numerator and the denominator by a quantity so that the number underneath the radical is an exact root. So we have the square root of 9 over 5. We can rewrite this as the square root of 9 over the square root of 5. We know that the square root of 9 is equal to 3, but we still have the square root of 5 here. So what we want to do is we need to multiply. See, our index is 2. When it's not written, we know that we have an index of 2. So we're looking for perfect squares underneath the radical in order to reduce the radical. So we're going to multiply both the top and bottom by root 5. Why do we do this? Is because we can write our top now as 3 times root 5. And because of our product property, we can put this back together. And we're left with the square root. I just put the 2 there. It doesn't need to be there. The square root of 25. We know that the square root of 25 is 5, so our answer is 3 root 5 over 5, and that's our answer, and it's the simplified radical. All right, if we look at our next example here, we have, let's see, We have the cube root of 2 over 9. We can rewrite this again. So we have the cube root of 2 all over the cube root of 9. We know that we can do this because of our quotient property of radicals. So what we want to do is, all right, so notice that we have a cube root right here. So we need groups of 3 or groups of 3, 9 here. So if we simplify our 9, we have 3 times 3. So what we really have here is the cube root of 2, and this is all over the cube root of 3 times 3. So in order to simplify this, we need to multiply both the top and bottom by root 3. What this does is now we have the cube root of 2 times 3 up here, and now we have the cube root of 3 times 3 times 3. And since we're taking the cube root, we're looking for 3 groups of 3 underneath the radical. We have a group of 3 3's, so we can bring a 3 out. So we're left with the cube root of 6 all over 3, and that's your simplified radical. Remember, you can always pause and stop the video in case you need more time to write out an example, or you need to go back and see something else again. But moving forward, we're going to do about 4 examples today. So if we look at our first example, we have the square root of 198. The first thing we want to do is, first of all, we notice that we have an index of 2, so we're looking for perfect squares. So the first thing is we're going to factor this into its prime numbers. So 198, we can divide into 9 and 22. Notice that both of these are not prime yet, so we can factor our 9 into 3 and 3, and our 22 into 2 and 11. So rewriting our radical, we can write this as the square root of 2 times 3 times 3 times 11. And because our index is 2, we're looking for groups of 2 of the same numbers. Notice we don't have 2 2's, so we're going to keep the 2 underneath the radical. We have a pair of 3's here. We're going to bring a 3 out in front. So we have 3 times 2 times 11. Notice I didn't bring an 11 out because there wasn't a pair of them. So our simplified answer is going to be 3 times root 2 times 11 is 22. So our answer is 3 root 22. All right, and if we move on, moving on to our next problem here, let me just change color. All right, so we have 3 root 54. Notice that 54 is not a prime number. We need to simplify this in order to simplify the whole radical. So the easiest thing to do is break it down into its prime factors. So we can break 54 down into 9 and 6. Still not prime, so we have 3 times 3 gives us 9, and 2 times 3 gives us 6. So if we move over here, we'll rewrite our radical. Don't forget your 3 coefficient out in front to begin with. So we have 3 times 2 times 3 times 3 times 3. We had 3 3's and 1 2. So because we're dealing with an index of 2, we know we're going to need pairs of 2. Notice that we only have 1 2, so that will stay underneath the radical. We have a pair of 2's here, so we'll bring out a 3 out in front. So we have 3 times 3, this original 3 from our original 3, and then we have 2 times 3, what was left underneath the radical. So 3 times 3 is 9, and we're left with square root 6. All right, now we don't always have to deal with just numbers underneath the radicals. We can also deal with integers, or not integers, some variables. So if we do a couple examples of those, if we look at number 3, we'll notice we have the square root of 128 times x to the 4th times x to the 3rd. So the first thing you want to do is break up your 128, your coefficient here. So if we break up 128, we can write this as 2 times 64. We can break 64 up into 8 times 8. We can break this up even further, but if we just leave it like this, because we have 2 8's, we know we can pull an 8 out. Also notice we have 4 x's since it's x to the 4th, and we have 3 y's since it's y to the 3rd. So if we rewrite our radical, we have 2 times 8 times 8. We also have 1, 2, 3, 4 x's and 3 y's. 1, 2, 3. So looking for perfect squares, because we're dealing with that index of 2, Notice that we don't have a pair of 2s, so it'll stay there. But we do have a pair of 8s, so an 8 will come out. Right. We have one pair of x's, we'll bring an x out. We have another pair of x's, bring another x out. We have a pair of y's, bring one y out. And notice we don't have another y to pair this with. So we are stuck with the 2 and y still underneath our square root. So if we simplify this, we're left with 8 times x squared, x times y, times the square root of 2y. And that's your simplified radical. All right, and if we do one more example today, notice that we're multiplying these two expressions together. Right. So what we're going to do is we know, because of the product property, that we can just multiply what's underneath together. So if we take a look at this, we have 24 times 12. That's going to give us, if we rewrite our radical here, notice it's an index of 2, so we'll be looking for perfect squares. So 24 times 12 gives us 288. We have x to the 6 times x. We know when we're multiplying like monomials, we add their exponents. So we have x to the 7th, y to the 3rd times y gives us y to the 4th. All right, so this just looks like just exactly what we did. We can break our 288 down into 2 times 144. And we know that 144 we can break down into 12 and 12. You could break this down even further, but notice since we're dealing with an index of 2, we're looking for pairs of numbers, and we have a pair of 12s here, so we'll leave it like that. So if we rewrite our radical, we have 2 times 12 times 12, and then we have x to the 7th and y to the 4th. So we have 7 x's and 4 y's. So looking for pairs of numbers, we have 1, 2, so that stays there. We have 2 12s, so we'll bring a 12 out in front. And so why I did not write all these out was because if we have 7, we want pairs of 2, so if we go down 1, we have 6. So 6 divided by 2 is 3. So we have x cubed out in front, and we're going to be left with 1 extra in our square root. And then we have y to the 4th, divide 4 by 2, we get y to the 2nd, and then we're left with what we still have underneath the square root. So that's 2, and remember we still have 1 extra x there. So that's going to be your answer. All right. And if you have any questions, please bring them to class. And remember to stop by Schoology and take your quiz. And have a nice night.